Look up. In almost every major city on Earth, a quiet revolution has taken place, one that has redefined our horizon and reshaped how we live, work, and connect. Skyscrapers. These aren't just buildings. They're magnificent monuments to human ambition, engineering brilliance, and our relentless drive to reach for the clouds. But how did we get here, and what makes these structures possible? The story of the skyscraper began not with a dream of height, but with a technological convergence in the late 19th century. Until then, buildings were limited by the crushing weight of their own walls. Masonry could only go so far before the ground-level walls became impossibly thick. Two crucial breakthroughs changed everything: the mass production of strong, reliable steel and the invention of the safe elevator. Steel frame construction was the game changer. Suddenly, instead of thick, load-bearing walls, buildings could be supported by a skeleton of steel beams and columns. This lightweight, incredibly strong frame allowed buildings to rise significantly higher. It wasn't just about strength, it was about efficiency, opening up floor space and allowing for large windows that let light pour in. Enter Elisha Otis and his safety elevator. Demonstrating his invention at the 1853 World's Fair, Otis dramatically cut the rope of his elevator, only to be saved by his patented safety brake. This single innovation gave people the confidence to embrace high-rise living and working. The quintessential early skyscrapers began to appear in Chicago and New York. The 10-story home insurance building in Chicago, built in 1885, is often cited as the first, with its internal steel frame. Soon, iconic structures like the Woolworth Building and the magnificent Empire State Building pushed the limits, redefining the very concept of a city's density. When we talk about what makes a skyscraper stand tall, we're talking about a symphony of materials. For decades, steel was king. Its immense tensile strength, its ability to resist being pulled apart, and its impressive compressive strength made it ideal for both horizontal beams and vertical columns. However, modern skyscrapers often rely on a more complex mix. Reinforced concrete, strengthened internally with steel bars or rebar, has become dominant. It offers exceptional compressive strength and is relatively cheap and versatile, easily molded into complex forms on site. But perhaps the defining material of the modern skyscraper isn't steel or concrete, but glass. The curtain wall, pioneered in the early 20th century, isn't a structural, load-bearing wall. It's a non-structural outer covering that simply hangs from the building's frame. This wall of glass and aluminum protects the interior from the elements, but also offers stunning, floor-to-ceiling views and maximizes natural daylight. This combination of a rigid structural core, perhaps a steel frame, and a lightweight curtain wall allowed buildings to become taller, lighter, and more energy efficient. The construction of a skyscraper is a monumental logistical and engineering puzzle. It all starts deep underground, with foundations. Because skyscrapers are top-heavy and subjected to immense wind and, in some places, seismic forces, their foundations must be anchors of incredible strength. Engineers often drive massive concrete and steel piles deep into the bedrock, or construct enormous concrete mats to distribute the building's enormous weight. Only when the foundation is secure can the structure begin its upward ascent. The actual building process is fascinating. You've likely seen the construction creep upwards, floor by floor, a dance of steel, concrete, and workers. But how do you get all that material and machinery up hundreds of meters? This is where one of the most remarkable machines in all of construction comes in: the tower crane. These are not built at the bottom and then somehow lifted. They are designed to grow with the building itself. A specialized climbing frame, or jumping form, surrounds the top section of the crane mast. When the crane needs to go higher, This frame uses powerful hydraulic jacks to lift the entire upper assembly, the jib, the cab, the counterweights, up one section at a time. New mast sections are then inserted and bolted into place, allowing the crane to build its own ladder. This constant self-lifting process allows cranes to operate at staggering heights, precisely maneuvering massive steel beams, precast concrete panels, and all the essential equipment needed to assemble the skyscraper. At the very heart of almost every modern skyscraper, both physically and functionally, lies the lift shaft. More than just a convenience, it's a critical structural element. This vertical concrete or steel tube isn't just for housing the elevator cabs. It often acts as the building's rigid spine or core. This reinforced core provides immense torsional and shear resistance, helping the building withstand the immense twisting and lateral forces generated by wind. It's often where you'll also find the building's essential services: stairs, water, power, and communications cables. The elevators themselves are masterpieces of engineering. To serve buildings with 100 or more floors, simple one-car systems are hopelessly inefficient. Instead, engineers design complex multi-car systems using destination dispatch technology. You enter your floor number on a keypad in the lobby, and the system instantly assigns you to a specific elevator car. This optimizes the flow, minimizes stops, and ensures people get to their destinations as quickly and efficiently as possible. Skyscrapers are far more than just architectural statements. They are intensely functional structures designed to solve the challenges of urban density. Their primary function, historically, has been commercial office space. By stacking offices vertically, corporations could concentrate thousands of employees in a single location, fostering collaboration and maximizing efficiency, all on a relatively small footprint. The classic open-plan office was, in many ways, born in the skyscraper. However, the modern skyscraper is increasingly multi-use. Many of the world's most iconic supertalls are vertical cities, blending luxury residential apartments, world-class hotels, high-end retail malls, and even public observation decks. This mixed-use approach creates vibrant, 24-hour vertical communities where people can live, work, and play, all within a single, soaring structure. It's a remarkably efficient way to utilize scarce urban land, reducing commute times and energy consumption. One of the greatest challenges facing any tall building, especially in seismically active regions, is earthquakes. The goal isn't just to make the building strong enough to resist the shaking. That would require an impossibly massive structure. The goal is resilience. Modern earthquake proofing is about absorbing and dissipating the energy. Engineers use ingenious systems like base isolation, where the building sits on massive bearings or pads made of lead and rubber. These act like giant shock absorbers, decoupling the building from the shaking ground. Another remarkable innovation is the tuned mass damper. Think of it as a giant, suspended pendulum, often weighing hundreds of tons, installed near the top of the skyscraper. When the building begins to sway from wind or a tremor, the damper swings in the opposite direction, exerting a counterforce that dramatically reduces the building's movement. Skyscrapers are an incredible mix of art, science, and necessity. What started as simple steel frames have become the icons of our cities and symbols of human ingenuity. When we look up, we aren't just seeing buildings. We're seeing a testament to our ambition and our ability to turn massive dreams into reality.